Alrighty, folks. Today we are going to wrap up our discussion of magnetism and its connections with electricity by talking about electromagnetic induction. So let's go ahead and get to it. Our learning target for today is I can describe the process of electromagnetic induction and its importance to our modern world. So for your notes set up today, I want you to have your topic be electromagnetic induction, and your essential question is how do magnets produce electricity? Go ahead and pause the video, set up your notes, and then come on back. All right, folks, so let's go ahead and define what do we mean by electromagnetic induction. So as we have shown when working with electromagnets, an electric current makes a magnetic field, and we know this because we've seen it with Ørsted's demo, with the wire producing the magnetic field, and then we've made solenoids and we've made electromagnets. But it turns out a magnetic field can also be used to make an electric current. And this is the process of electromagnetic induction, the process of generating a current by moving an electrical conductor in a magnetic field. So basically what is happening is called Faraday's law. A voltage is induced in a conductor by a changing magnetic field. All right, let's slow down and break that down to what that means. So remember that that voltage is a push that moves electrons. The electric potential that moves electrons. So a changing magnetic field, all that means is a moving magnetic field. So what we're saying is if you take a magnet, right here for example, and you moved it through this solenoid, as the magnet moved through, the electrons in the solenoid are going to be affected by the magnetic field because early on when we were talking about magnets, we talked about the fact that magnets affected electric charge. And so as you move that magnet through the solenoid, the electrons in that solenoid, they are going to be affected by the magnetic field and they are going to begin to move. They're going to be pushed. So remember, moving a magnet, that induces voltage, that's that push, and once you have voltage pushing electrons, then you have movement of electrons, and that is current, and now we have electricity. So when a magnet is in a coil of wire that is a part of a circuit, if either the magnet or the wire move, a current will be produced, and that is electromagnetic induction. So this is just an example of a circuit. A galvanometer is a tool that is used to measure how much electricity is being produced. So go ahead and pause this video and head over to the Nearpod, and I want you to watch this video that explains how this process works. It's an awesome video because it is old and it has awesome animation and cool audio. So check that out and then come on back. All right, so hopefully that helped clarify some things. What question do you have about what question do the previous slides answer? All right, so generators. Most electrical energy that we use is produced in power plants using generators. And a generator is a device that converts mechanical energy, motion, into electrical energy by rotating a coil of wire in a magnetic field. So just think about the fact we were talking about electromagnetic induction, where you move the magnet. Well, as we said, as long as something is in motion in a magnetic field, whether it's the magnetic field itself or the wire, that induction of electricity will happen. So in a generator, we move the coil of wire in a set magnetic field, and the motion of this coil produces the electric current. And the cool thing about generators is you can use all sorts of tools and energy sources to power that generator, to move that coil in the magnetic field. You can use a human just standing there cranking it. It's a hand crank generator. You can produce steam, and that steam turns a wheel, which then turns the coil in the generator. And that steam can be produced from fossil fuels. It can be produced from nuclear energy. A lot of different ways to produce energy that will turn a generator. And there are two types of generators: AC and DC, or alternating current and direct current. What question does the previous slide answer? All right, so let's go ahead and start off with the simplest type of generator, and it is called an AC generator. An AC generator produces alternating current in which the current changes direction constantly. So this would be an example of an AC generator. What we have here is we have a loop of wire, and it is connected to a handle, and it's placed between two magnets. Your north pole of the magnet here, your south pole of the magnet here, and it is rotated. And you will see that this loop of wire is connected to these metal rings. And so this one right here on the right is connected to this first metal ring. This one on the left is not touching that first metal ring, but is touching the second metal ring. And then those are connected to the circuit. And so, as we said, that's kind of what's happening. The two conductive rings connect to a circuit. And so basically what happens is you rotate this, and the wire moves between or in the magnet, and it's rotating. And so it's in constant motion between the magnets. And because it is in constant motion here, that is going to cause the electrons to begin to move. And they are going to then travel in the circuit. So if you know anything about motors, this is effectively an electric motor in reverse. Now, here's the thing that happens. So you see how right now this part of the wire loop is facing the north pole of the magnet, and this part of the loop is facing the south pole of the magnet. So here's the deal. When this happens, when the loop is exposed to the north side of the magnet, the electrons move in one direction, and when it's exposed to the south pole of the magnet, the electrons move in the opposite direction. So here's what happens. When it is over like this, the wire loop, the current flows, let's say, from here and over to this side. And so that's the flow direction of your current. However, when the loops change sides, all of a sudden, the loop that was on the south side and it was moving the electrons in one direction, it is now on the north side, and vice versa. And so the electrons change their direction. So now you would just have to imagine that this flipped, and now the electrons are traveling in this direction. And so as a result, the current in an AC generator, it doesn't just flow like a river, if you will, in one direction. Instead, the electrons kind of shake. And that movement is current, and that does work. So that is a type of current, and that's AC, or alternating current, in the sense that the direction of the current alternates as frequently as the loop moves. What question does the previous slide answer? So, a DC generator, or direct current generator, is basically the same concept as an AC generator, except it produces direct current. So, as the loop rotates, just like before, an alternating current is induced in the wire. However, this time, instead of the wires being attached to these static rings that just stay still, there's a commutator. So basically, two C-shaped pieces of metal that connect to the loop. And so as this rotates, and the two pieces of metal are not connected, and then the commutator touches the other side, or the two sides of the circuit. And so as it rotates, the direction of the circuit is changing constantly, but it changes as the wire's position between the north and south pole of the magnet change. So whatever is touching this side of the circuit will always be exposed to the north side, or the north pole of the magnet, and whatever's touching this side of the circuit will always be exposed to the south side of the magnet, because this C-shaped ring, it will rotate, and by the time it reaches this circuit, this blue part of the wire is now over towards the north side, and this red part of the wire is over towards the south side. And so as a result, the flow of electrons will stay in the same direction. So, since the current and circuit are constantly changing direction, they cancel each other out, and you get a current moving in one direction. So, the big thing here is to know that a commutator is two C-shaped pieces of metal at the end of the wire in a DC generator that converts alternating current to direct current. All right. go ahead and pause this video. Once again, head over to Nearpod, check out this awesome thing from the 70s, I think probably, this cartoon that helps explain alternating and direct current generators. What question do the previous slides answer? Alrighty, folks. So that's it on electromagnetic induction. Go ahead and pause this video, go through, try to answer the questions in the Nearpod quiz, and then come back and we'll go through the correct answers. All right, in order to induce a current in a wire, you must have the following things. You need to have a magnet, and you need to have a conductive material, which is usually going to be some type of wire, but it does not have to be a coil, and you need to have motion. A device that converts mechanical energy into electrical energy by rotating a coil of wire in a magnetic field, that would be a generator. As a loop of wire is rotated between two magnets, it produces a current which changes direction constantly. This is an AC or alternating current generator. That changing direction, that tells us it's alternating. And if you add a commutator, two C-shaped pieces of metal that constantly change direction as it turns, to an AC generator, it becomes a DC or direct current generator. So if you answered all of the questions like that, you should have gotten 100%. All right, folks, go ahead and self-assess on a scale of 1 to 5. How well do you understand electromagnetic induction? Alrighty, so what you need to do, I will post some videos to review on Schoology. If you are 1 or 2, that'll help you hopefully grasp this concept a little bit better. Once you get up to 3 or 5, or 3 to 5, I want you to head over to your packet, and in your packet towards the end, there is a electromagnetism review. And there's a bunch of questions, so I want you to go through those and make sure that you understand electromagnetism. And if you feel like you don't understand one of the questions or need some help, please reach out to your teacher, and we'll be very happy to help you. Alrighty, folks, have a great day.